every single day, you walk into offices, live in apartment buildings, and drive over bridges without giving it a second thought, right? We just trust that they're all going to stay up. But here's the thing, that trust isn't based on luck. It's built on a massive, incredibly detailed, and almost completely invisible rulebook. And today, we're going to pull back the curtain and show you its secrets. So, what is this master plan, this hidden document that every single engineer and builder has to live by? It's like the silent guardian of our entire modern world, and it's time we finally got a look at it. And here it is, ACI 318-19. Okay, I know, it doesn't exactly have a blockbuster name, but believe me, this document is the literal foundation of modern construction. And calling it a building's DNA, that's not an exaggeration. Every beam, every column, every floor slab, its genetic makeup is defined right here in these pages, making sure it grows up strong and safe. So here's our game plan. We're going to decode this thing together. First, we'll talk about what the code really is. Then we'll look at the materials it controls. After that, we'll dive into how engineers use it to fight physics itself, how it preps for disasters like earthquakes, and finally, how it all comes to life on a real construction site. All right, first up, the code as a building's DNA. See, this thing isn't just a list of do's and don'ts. It's a universal language. It means an engineer in California and a contractor in New York can look at the exact same set of plans and know with absolute certainty what it takes for a column to be considered safe. Now, here's what's so brilliant about how this document is set up. The code itself, that's like the law. It gives you direct, unchangeable commands. But right next to it, you have the commentary, which explains why. It's this perfect system. One part gives you the strict rule, and the other tells you all the deep scientific reasoning behind that rule. You get the what and the why. So, how does this code actually apply in the real world? Well, it starts with the most basic ingredients of our buildings, concrete, and its essential partner, steel reinforcement. And the code is incredibly specific about both of them. Just look at this table. This gives you a perfect idea of the insane level of detail we're talking about. This comes right out of the code's appendix. A piece of rebar isn't just some random metal rod. A number 8 bar, for example, has to have a diameter of exactly 1 inch and weigh precisely 2.67 pounds per foot. This standardization is absolutely non-negotiable, and it means an engineer in Miami is designing with the exact same building block as an engineer in Seattle. And it's not just about the materials themselves on day one. It's about how they're going to hold up for decades. The code has entire sections just for making sure a parking garage in a snowy climate can handle years of freezing, thawing, and road salt without falling apart. The code is literally planning for a 50-year lifespan, making sure the relentless cycle of winter doesn't slowly turn a solid structure into dust. Okay, so you have your perfect standardized materials. Now what? Now you have to design a structure that can fight a constant, invisible war against all kinds of forces: gravity, wind, even the weight of people and furniture. This is where the code becomes the battle plan. The core principle is actually pretty simple, but it's also profound. First, engineers have to calculate all the possible forces a building could ever face in its entire life. Then, the code makes them multiply those forces by safety factors, so they basically inflate the number. That new, bigger number is the required strength. And that one rule, right there, is the fundamental promise of structural engineering. The design strength always has to be greater than the required strength. It's not about being just strong enough. No way. It's about having a deliberate, calculated margin of safety built into every single piece of that structure. Now, let's look at a special case where those forces are extreme and totally unpredictable: earthquakes. A building shaking violently is a completely different problem than a building just sitting still, so the code has an entire chapter dedicated just to seismic design. And the first thing the code recognizes is that earthquake risk isn't the same everywhere. Right? A building in a hot zone like San Francisco is facing a totally different threat than one in a stable region. So the rules are not one size fits all. They are tailored specifically to the local risk. The code handles this with something called seismic design categories, or SDCs. It's pretty simple. The higher the letter, the bigger the risk, and the tougher the rules get. A building in SDC D, E, or F is going to have way more steel and much stricter requirements. It's all about making sure the level of safety matches the level of danger. And this right here, this is a crucial secret hidden inside the code. It turns out it's not just the raw power of an earthquake that's so dangerous. It's the cyclic loading, that relentless back and forth shaking. It's way more brutal on concrete than a steady push. So to fight that, the code demands extra steel to make sure the building has ductile behavior, which basically means it can bend and sway without snapping. It's designed to absorb the quake's energy, not just fight it head-on. Look, all this amazing theory is great, but it means absolutely nothing if it isn't built correctly. And that's why the code doesn't just stop at the design phase. It follows the project right out onto the construction site to make sure those plans become a safe reality. Check out this simple hook. It looks like such a minor detail, but its exact shape, the curve of the bend, the length of the tail, is spelled out precisely in the code. Why? Because this little hook is what anchors the steel skeleton firmly inside the concrete, letting them work together as a single team. If you get this tiny detail wrong, the whole system could fail. The code actually requires a chain of custody for safety. It starts with the design, sure, but then it demands quality control at every single stage. You have to test the concrete that comes to the site, you have to verify the steel is in exactly the right place, and you have inspectors constantly checking the work before the building gets a final green light. And this is a really crucial point. As the concrete trucks are literally pulling up to the job site, samples are taken. They're put into these little cylinders, which are then taken to a lab and crushed by a machine to prove that the concrete is as strong as the engineers said it needed to be. It's a critical, real-world check that makes sure the design strength we talked about isn't just a number on a page, it's a physical reality. And in the end, it all comes down to this one powerful idea. One single unified code, one shared language for safety. Because this one document is adopted and enforced across the country, it creates a system that lets us build these incredible, complex structures with a level of safety our ancestors could only dream of. So the next time you step into a skyscraper or cross a bridge, just take a second. Think about the hundreds of pages and thousands of rules, the hidden DNA of ACI 318, that are all working silently, together, to make sure the ground beneath your feet is solid and the roof over your head is secure.